Okay, in the last lecture we have discussed about the algorithm for signed multiplication. Okay. So, today we will map the algorithm onto the architecture. Okay. So, what is the architecture for signed multiplier? So, in order to map this algorithm onto architecture, first we have to define a processing element. Okay. So, here I am going to define processing element as this. So, with A in is the input, A out is the output, and I will make A out is equal to A in. Similarly, B in is the input, B out is the output, I will make B out is equal to B in. Then the carry input, we are going to apply here C in, C out, and here we are going to use some input S in, and this is S out. So, this S out plus C out we are going to write combinedly, S out plus C out is equal to S in plus C in plus A in B in. So, basically this is a full adder. Okay. So, this A in B in is a single value 0 or 1. Okay. So, the meaning of this one is S in is one input, C in is another input, S in is applied here, C in is applied here, and A in B in you can obtain by taking the AND gate between this A and B in. By passing through the AND gate you will get A in E in. So, by passing A in and B in through the AND gate you will get A in B in. So, this is a single value A in B in, a single value, this can be 0 or 1, this is output of the AND gate. If we add 3 bits you will get outputs as 2 outputs, which is S out, C out, that is the meaning of this. So, 0 0 0 sum is 0, carry is 0, 0 0 1 sum is 1, carry is 0, exactly same as the full adder. Okay. This processing element here is basically a full adder. So, 0 1 0 1 0, 0 1 1 0 1, because the carry will be generated 1 0, 1 0 0 1 0, 1 0 1 0 1, 1 1 0 also 0 1, 1 1 1 is 1 1. This is the meaning of this definition. Okay. Now, using these processing elements we have to construct the parallel multiplier. Basically, we have taken the multiplication of A as A3 dot A2 A1 A0, B as B3 dot B2 B1 B0, and Y we are taking as AB. This also I am storing only 3 bits, Y3 dot Y2 Y1 Y0. Okay. Here I have given in general as A in can be either A0, A1, A2, A3. Similarly, B in can be B0, B1, B2, B3. So, because we have 4 A's and 4 B's, so totally we need 16 such processing elements. Okay. If I take the overall architecture of this one, this is one processing element, this is another processing element, another processing element. So, we are going to repeat the same processing element throughout the system. So, this is called modular architecture. So this particular array is called systolic array. We have total 16 such processing elements. I will explain the operation with the help of the algorithm that we have developed in the last lecture. These are 16 processing elements. So basically A's we are going to give in this direction, B's we are going to give in this direction. Okay. So here this is A0 will give here. So this line is also A0 because A out is equal to A in. This is also A0. This is also A0. But here A0 we have to apply through the NOT gate. I will tell you what is this A0 bar in fact. A0 bar. So I will tell the reason why this should be A0 bar. Okay. Similarly, if I apply A1 here, this is also A1, this is also A1, this is also A1, but for the last one I will apply A1 bar. This is A1 bar. This is A2, output is also A2 because I am defining this processing element such that output of A is equal to input of A. A2, but here we have to give A2 bar. Similarly, here A3 bar. Similarly, here B0. So this entire line is B0. This is also B0. This is also B0. If I take output here also this will be B0. This entire line is B1 line. B1, B1, B1 and B1. Similarly, B2, 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 B2. So totally we need 16 product terms. Okay. That is why we require 16 processing elements. This is B3. This is B3, this is B3, B3, this is also B3. So this is about A's and B's connection. Okay. And what about this sum and carry connections? This is C in here. I will make this as 0 and this is C out. This is C out. This C out plus this S out is given by this relation. So the initial carries for all these things except the last stage I will give as zeros. Now this scene I will connect to B3. I will explain why this has to be connected to B3. Now some bits, here I am going to give 0, here I am going to give 0, sum in, this is also 0, this is also 0. Then the output of each one we are going to connect here. Here this will give some output, this will give some output. Here also will be having sum in, sum in. Now to get this the final connections of this one, so we will refer back to the algorithm that we have discussed in the last lecture. So this was the algorithm that we have developed using Horner's law. So to perform the signed multiplication of two 4-bit numbers A3, A2, A1, A0, B3, B2, B1, B0. Okay. So the procedure is here. First we have to compute AB0 and then AB0 into 2 raised to the power of minus 1. In that we have to lose this, we have to neglect this and we have to extend the sign of these bits. Similarly, step by step procedure, first we will find out this AB0 into 2 raised to the power of minus 1, then add this, again 2 raised to the power of minus 1, add AB2, again 2 raised to the power of minus 1, finally add minus AB3. So A0, B0, basically here this should be A0, B0. We can see that here, what is the output here? If I call this as the processing element for this definition of the processing element, what is the output of this first processing element? S out plus C out is equal to S in plus C in plus A0, B0. Okay, for this particular processing element. If I call this as processing element 1, for processing element 1, what is S out plus C out is equal to S in plus C in plus A0, B0, because the inputs are A0, B0. And what is S in? 0. What is C in? 0. So this is simply A0, B0. So what does it mean? So only some bit is A0, B0, there is no carry at all, because only this A0, B0 is single bit. Okay, this can be 0 or 1. So some bit is A0, B0, this is some bit. So this we are going to discard, because if you want to store 8 bits of the result, here I am storing only 4 bits of the result. If I want 8 bits of the result, I can store these values also. Okay. So here what I am discarding this. This is sum we are going to discard, and what is this carry? This carry is 0, because this is only single value which is either 0 or 1, which is sum itself. So this is something like A0, B0 plus 0. If I perform this, A0, B0 can be 0 or 1. Okay. So what is sum bit and carry bit? 0 plus 0 is 0 only, sum bit is 0, carry bit is also 0. If you want to write 2 bit equivalent, 0 plus 1 is, in decimal this is 1, what is the binary equivalent? 0, 1, means this is sum bit and this is carry bit. So this is 0. Now what about this value, the output of this? So I will write now these values. So for this processing element, what are the inputs? This carry is 0, this sum is 0, so output is simply the inputs. This is B0 is the input and A1 is the input. So output of this one is A1, B0. Of course this carry is 0. And what about the carry? Here also same thing, for this processing element, if I call as 2, for processing element 2 also, what will be the input? S out plus C out is equal to S in plus C in plus what are the A's and B's for this second processing element? A is A1, B is B0. Okay, A1, B0. But this S in is 0 plus this C in is 0 plus A1, B0. So, always only this bit is sum bit only, carry bit is 0. That means implies S out is simply A1, B0 and C out is 0. So, this C out is also 0. This S out is A1, B0. Similarly, you can find out output of this processing element as the sum bit will be 0, carry bit will be, the inputs is A2, B0. This is A2, B0. Similarly, this will be A3, B0 and this carry output is 0. Okay. So, we have generated A1, B0, A2, B0, A3, B0, A0, B0. In that A0, B0 I have discarded. So, whatever this the first this row A0, B0, A1, B0, A2, B0, A3, B0 I have generated using the first 4 processing elements. In that A0, B0 is discarded. Okay. Now, in the second row what is to be added to this one? So, I have to add this I have discarded. For A1, B0 I have to add A0, B1, for A2, B0, A1, B1 and so on. And this A3, B0 has to be extended to the sign. Okay. This A3, B0 has to be added with A2, B1 as well as A3, B1. Okay. Now, I will show that one. Now, this thing is A1, B0 is generated, A0, B1 you have to add. So, coming for this processing element. So, what are the inputs? A0 is this input, this B1. Okay. So, sum in for this, if I call this one as 1, 2, 3, 4, the fifth processing element. For fifth processing element, you can see sum in is equal to S in, you can call as sum in is S in. S in is equal to A1, B0, A1, B0 and C in is we have applied as 0. So, therefore, S out plus C out is equal to S in plus C in plus what is A and B that is applied for this fourth one. A is A0, B is B1. So, plus A0, B1. So, this will be C in is 0. So, this is A1, B0 plus A0, B1. Okay, this will get some sum term as well as carry term. Okay, what is sum bit and what is carry bit of this? So, if I add these two, sum bit is PP01 and carry bit you have to propagate and you have to add here. Okay. So, sum bit of this stage is PP01, that also we are going to discard. So, the sum bit of this processing element 5 is PP01, this also we are going to discard. And carry bit we are going to, this carry bit is not 0. So, this is carry of, this bit is carry of A1 B0 plus B1 A0. Okay, that we are going to add in the next stage. So, this carry of this one we are going to add in the next stage. Okay, this carry whatever is generated, sum is discarded. Okay. So, now in the third stage we have to add A2 B0, A1 B1 and then the carry of the previous one, sum of that one is PP11 and carry again you have to propagate to next stage. You see here, if I take the processing element 6, so what is the output? Sum bit. So, of course, here you have this to connect to sum here. Okay. So, what is the sum bit of this P6? So, this is carry of this one previous bit, and these bits are, the sum bit is A2 B0 and this is A1 B1. A2 B0 plus A1 B1, A2 B0 plus A1 B1 plus the carry. This is going to perform in the processing element 6. Okay. A2 B0 A1 B1 plus the carry from the previous stage, this one, this carry from the previous stage, this is not 0. Okay. So, what is the sum bit of that one? Sum bit of this one will be this PP 11, carry bit you have to propagate to the next stage. Again this sum bit has to be added with A0 B2, A0 B2. This is A0 B2. Okay. Whose sum bit is PP02, this you have to neglect or discard, PP02. So, PP02 will be generated here, this also you are going to discard. So, like that we will proceed. So, at the last stage, here you see this A3 B0 has to be added with A2 B1, A3 B0 has to be added with A3 B1 also. Okay, A3 B0 has to be added with A3 B1, A2 B1. Okay. So, A3 B0, A3 B0 has to be added with A2 B1, A3 B1, A2 B1, A3 B1. A2 B1 is this one, A2 B1 is this one, we have to add here. Anyhow, we are adding this A3 B0, we are adding with in this processing element A2 and then correspondingly B1. The output of this processing element is A3 B0. So, in this processing element what addition will be performed? A3 B0 plus A2 B1, of course, the carry from the previous stage also. The other one is A3 B0, we have to also add with A3 B1, right, A3 B1. So, this sign extension, this A3 B1 also you have to add. So, what you have to do is same A3 B1 you take from here and you connect to the this one. This will show the sign extension of sign extension connection. Now, the same A3 B0 is going to add with A2 B1 as well as A3 B1. This is A3 B1, this is A2 B1. So, that is what we have here, A3 B1, A2 B1. Similarly, this PP31 has to be added with A2 B2, A3 B2. So, that we have to do in a similar manner. So, this is PP this one. So, this has to be added with both A2 B2 as well as A3 B2. So, this is the connection, sign extension. Similarly, here also this has to be added with this. So, this connection will be, this value will be PP31 and this will be PP22. This is PP31, this is PP22, you can easily check this. So, the PP31 has to be added with two values, that is A2 B2 as well as A3 B2. A2 B2, A3 B2. Similarly, PP22 is A2 bar B3, A1 bar B3. This is A2 bar B3 and A3 bar B3. Okay. Now, there is one extra term like this B3 has to be added along with this PP11, A0, B0, and we have to add B3 also, whose output is Y0. Okay. So, this addition of the B3 is nothing but, you can see that this is B3. So, instead of making this C in is equal to 0, if I connect this B3 to C in, so C in becomes B3, so that the third bit that will be added will be B3. So, this one will be implemented by connecting this B3 bit to the carry in is equal to B3. Okay. So, here we will get Y0, Y1, Y2, Y3. So, you see about the signed multiplier architecture, just I have mapped this algorithm onto architecture. This algorithm what I have developed in the last lecture. So, we just mapped this onto the architecture. Okay. These are 4 bits. If you want to retain these bits also, then you can increase the accuracy. Okay. Otherwise, you can neglect also. Okay. So, this is about the complete signed multiplier architecture. But the drawback of this one is this is more complex. Due to sign handling problem. So, we have to take the sign bit, we have to extend the sign of this one. So, because of that this is more complex. So, to avoid this sign handling problem, okay. So, there is one efficient signed multiplier called Baugh-Wooley multiplier. Okay. So, next we will discuss about the Baugh-Wooley multiplier, and using Baugh-Wooley multiplier you can implement the filters. This is also signed multiplier, but this will take less complexity. How the complexity of this multiplier is reduced? Okay. So, we will see now using some mathematical background. So, we will take the same A is 4 bit number A3 dot A2 A1 A0 in binary form, and in decimal form this is minus A3 plus A2 to raised to the power of minus 1 plus A1 to raised to the power of minus 2 plus A0 to raised to the power of minus 3, and B is B3 dot B2 B1 B0 in decimal form minus B3 plus B2 to raised to the power of minus 1 plus B1 to raised to the power of minus 2 plus B0 to raised to the power of minus 3. So, we want y is equal to AB. If I take the decimal values, this will be minus A3 plus A2 to raised to the power of minus 1 plus A1 to raised to the power of minus 2 plus A0 to raised to the power of minus 3 into minus B3 plus B2 to raised to the power of minus 1 plus B1 to raised to the power of minus 2 plus B0 to raised to the power of minus 3. Here we will do some manipulation, thereby we cleverly handle the sign involvement. Okay. This is equal to minus A3 minus B3 becomes A3 B3. So, there is no sign here. Okay. So, the only terms where the sign is involved is minus A3 if I multiply with this one, and minus B3 if I multiply with this one. These two are having the negative signs. Minus A3 with B2 2 raised to the power of minus 1 plus B1 2 raised to the power of minus 2 plus B0 2 raised to the power of minus 3 minus B3 A2 2 raised to the power of minus 1 plus A1 2 raised to the power of minus 2 plus A0 2 raised to the power of minus 3. So, remaining thing is all positive terms. So, what is that? Plus remaining thing that is left is this into this A2 2 raised to the power of minus 1 plus A1 2 raised to the power of minus 2 plus a naught 2 raised to the power of minus 3 into b2 2 raised to the power of minus 1 plus b1 2 raised to the power of minus 2 plus b naught 2 raised to the power of minus 3. So, the only problem with these two terms which are having minus sign. So, I will consider only this minus sign terms first. I will do some manipulation, later I will come to this final expression. Okay. So, let us consider this minus I am taking outside, a3 this one, b2 2 raised to the power of minus 1 plus b1 2 raised to the power of minus 2 plus b naught 2 raised to the power of minus 3. This becomes plus because I have taken minus outside, b3 a2 2 raised to the power of minus 1 plus a1 2 raised to the power of minus 2 plus a naught 2 raised to the power of minus 3. Here I am going to use some trick. So, this is equal to minus sign. First I will multiply as it is. What are the coefficients of 2 raised to the power of minus 1 is a3 b2 plus b3 a2. This whole thing is 2 raised to the power of minus 1. 2 raised to the power of minus 2 is this term and this term plus a3 b1 plus b3 a1. This whole thing is 2 raised to the power of minus 2, and 2 raised to the power of minus 3 term will be a3 b naught plus b3 a naught. Now, here I am going to write this as, if a is a Boolean variable, in general a is a Boolean variable, I can write a as 1 minus a bar always, because if a is 0, a bar is 1. So, this 1 minus 1 becomes 0. If a is 1, a bar is 0, this is 1 minus 0. Okay. So, always you can write a as 1 minus a bar. Okay. This is what we are going to write here. This is minus of, this I will write down as 1 minus a3 b2 whole bar, because this I will take as a single term. Similarly, 1 minus b3 a2 bar into 2 raised to the power of minus 1 plus 1 minus a3 b1 bar plus 1 minus b3 a1 bar into 2 raised to the power of minus 2 plus 1 minus a3 b0 bar plus 1 minus b3 a0 bar, whole thing into 2 raised to the power of minus 3. Now, what is the constant term? So, remaining thing is, we will have minus of this, I will take minus outside. Okay. So, if I take the constant term, this is minus of, so the first term is 2 raised to the power of minus 1 into 2 raised to the power of minus 1, and this one is 2 raised to the power of minus 2 plus 2 raised to the power of minus 2 plus 2 raised to the power of minus 3, and this minus sign if I take inside, this becomes plus, this minus of minus becomes plus, this minus of this minus becomes plus, this minus of this minus becomes plus, all becomes plus. Okay. So, we will get a3 b2 bar plus b3 a2 bar into 2 raised to the power of minus 1 plus a3 b1 bar plus b3 a1 bar whole bar into a2 raised to the power of minus 2 plus a3 b0 bar plus b3 a0 bar into 2 raised to the power of minus 3. Sorry, there is a mistake here. In fact, this is 2 2 into 2 raised to the power of minus 1. This is not singly 2. This is 1 plus 1 is total 2. 2 into 2 raised to the power of minus 1. Okay. This term is in fact, this is minus of 1 plus 1 is 2. 2 into 2 raised to the power of minus 1. Here also 1 plus 1 2 plus 2 into 2 raised to the power of minus 2 plus 2 into 2 raised to the power of minus 3. Okay. So, what happens now? So, this will be 2 into 2 raised to the power of minus 1 minus of becomes 1 plus this becomes 1, this becomes 2 raised to the power of minus 1 which is 1 by 2, this is 2 raised to the power of minus 2 which is 1 by 4. So, this is equal to minus of 4 plus 2 plus 1 is 7 by 4. This can be represented as 2 minus of 1 by 4. So, this 2 is overflow. And we have seen that the overflow in 2's complement can be neglected in between. So, this will become simply plus 1 by 4 which is equal to plus 2 raised to the power of minus 2. This is the logic that we are going to use to reduce the complexity of the system. Okay, because one of the properties of this 2's complement number is intermediate overflows can be neglected. That is what I have explained in the last lecture with example also. So, this entire term becomes only 2 raised to the power of minus 2. So, what happens is here, so this is equal to A3 B2 bar plus B3 A2 bar into 2 raised to the power of minus 1 plus 2 raised to the power of minus 2, here this term is also there. So, we will get 1 plus extra term. This is A3 B1 bar plus B3 A1 bar plus 1, because this entire thing is equivalent to 1 by 4 which is equal to plus 2 raised to the power of minus 2. That if we take common, this becomes 1 plus A3 B0 bar plus B3 A0 bar into 2 raised to the power of minus 3. So, this is this entire value. If you substitute this value here, so we will get y expression as A3 B3 is signed term plus we have 2 more terms. So, this term as it is A2 plus A2 2 raised to the power of minus 1 plus A1 2 raised to the power of minus 2 plus A0 2 raised to the power of minus 3 into B2 2 raised to the power of minus 1 plus B1 2 raised to the power of minus 2 plus B0 2 raised to the power of minus 3 plus the remaining thing we have simplified to this value. So, what is that? A3 B2 bar B3 A2 bar. A3 B2 bar plus B3 A2 bar into 2 raised to the power of minus 1 plus A3 B1 plus B3 A1 plus 1 whole bar into 2 raised to the power of minus 2 plus A3 B0 B3 A0. If you further simplify this and finally we will get the algorithm. From this expression we are going to develop an algorithm, then that algorithm we are going to map onto the architecture. Okay. So, what are this A3 B3 is as it is plus what are the coefficients of 2 raised to the power of minus 1, minus 2, minus 3 and so on. So, this is equal to here this is A2 B2 2 raised to the power of minus 2 plus A2 B1 2 raised to the power of minus 3 plus A2 B0 2 raised to the power of minus 4 plus a1 b2 2 raised to the power of minus 3 plus a1 b1 2 raised to the power of minus 4 plus a1 b0 2 raised to the power of minus 5 plus a0 b2 2 raised to the power of minus 4 plus a0 b2 2 raised to the power of a0 b2 2 raised to the power of minus 4 plus a0 b1 2 raised to the power of minus 5 plus a0 b0 2 raised to the power of minus 6 plus this entire thing. I am not writing this again. Okay. Now, overall final this value is a3 b3 plus, so what are the total 2 raised to the power of minus 1 coefficient. This is 2 raised to the power of 0 coefficient. What is 2 raised to the power of minus 1 coefficient? This one, 2 raised to the power of minus 1, here nothing is there, so only this one. So, this is a3 b2 bar plus b3 a2 bar 2 raised to the power of minus 1 plus 2 raised to the power of minus 2 is this one, and here also you have this term. Okay. So, this total term is a3 b1 bar plus b3 a1 bar plus 1 plus this term a2 b2. This one will be, this is 2 raised to the power of minus 2. 2 raised to the power of minus 3 is this, this and this. Okay. So, what are the total terms? a3 b0 bar plus b3 a0 bar, and here two terms a2 b1 plus a1 b2. This whole thing is 2 raised to the power of minus 3, and here there is no 2 raised to the power of minus 4, only these two terms. 2 raised to the power of minus 5 is these two terms, 2 raised to the power of minus 6 is only this term. So, what is the coefficient of 2 raised to the power of minus 4 is a1 b1 plus a0 b2. a0 b2 is 2 raised to the power of minus 4. 2 raised to the power of minus 5 is a1 b0 plus a0 b1 and a0 b0 2 raised to the power of minus 6. This is the complete expression for y. Now, I can map this onto the algorithm. So, if I take the algorithm a3 dot a2 a1 a0 into b3 dot b2 b1 b0. So, in case of Baugh-Wooley multiplier, so what is 2 raised to the power of 6 coefficient a0 b0, here a0 b0, simply this itself is p0, and 2 raised to the power of minus 5 is, here you will get two terms, one is a1 b0 and if I say multiply this with this one, and then you will get a2 b0, ordinary multiplication b0 a0, a1 b0, a2 b0, a3 b0, but this wherever this a3 or b3 is there, I will take the complement. Similarly, with b1, this one is a0 b1, a1 b1, a2 b1, a3 b1 bar, because a3 is there. So, whenever a3 is there or b3 is there, I will take the complement. Similarly, with b2, a0 b2, a1 b2, a2 b2, a3 b2 bar. Similarly, with b3, because b3 is there, all complements. So, this is b3 a0 b3 bar, because b3 is sign bit, a1 b3 bar, a2 b3 bar, and a3 b3 both are signed. So, there is no complement. So, if you see here now, so this one is coefficient of 2 raised to the power of 0, this one is 2 raised to the power of minus 1, because here dot will be there. This is 2 raised to the power of minus 2, this is 2 raised to the power of minus 3, 2 raised to the power of minus 4, 2 raised to the power of minus 5, 2 raised to the power of minus 6. You can easily verify this. 2 raised to the power of minus 6 is a0 b0, this will get as p0 final output, and P1 is 2 raised to the power of minus 1 term A1 B0 A0 B1, A1 B0 A0 B1, this is P1. 2 raised to the power of minus 4 term is A1 B1 A1 B1 A1 B1 plus A0 B2 A0 B2, and there will be one more term like A2 B0. Here somewhere A2 B0 is missing. So, here A2 B0 is also there. This A2 B0 is also there. So, plus A2 B0 into this one. This is P2. Similarly, 2 raised to the power of minus 3 is, we have A3 B0 bar, B3 A0 bar, A2 B1, B2 A1, this is P3. 2 raised to the power of minus 2 is, here we have to add a one extra also. This one A3 B1 bar, B3 A1 bar, then A2 B2. So, this is P4. Then 2 raised to the power of minus 1 is this A3 B2 bar, B3 A2 bar, P5, and last one is, this is P6. So, totally we will get 7-bit output. Okay. So, this is about the algorithm of this one. So, we can map this onto the architecture. So, we will discuss this architecture and then corresponding Verilog code in the next lecture. Thank you.